We're going to go through balancing of double displacement reactions. And if you recall from the intro lesson, in order to have a double displacement reaction, you need to have a compound plus another compound. Now, the compounds have to be ionic compounds and they need to be aqueous. So what that means is they have to be dissolved in solution. So, whenever we're looking at compounds, recall that the first part of the compound is always the positive ion, and the second part of the compound is always the negative ion. So, I'm just going to put a little plus and minus here. What I want you to know in a double displacement reaction, the positive ions just swap places. And remember that the positive always has to be written first. So that's why here, if the C and the A swap places, you will get CB and not BC. Okay? So outside hookup, inside hookup, or what you can do is just swap the positive ions there. So this is a generalized equation for double displacement reactions. Now let's take a look at an example where we have sodium sulfate and we have calcium nitrate. So sodium sulfate in its aqueous form and calcium nitrate are able to swap partners. So this is the positive ion in each case. We're going to hook the calcium up with the sulfate. We're going to hook up the sodium where the nitrate goes. So in doing so, I don't just write Ca2 because there's a 2 here for the sulfate. No, I have to go back and take a look on the periodic table. Calcium has a charge of +2, and this group here, sulfate, is a -2. We crisscross and we reduce and drop the brackets. And then we also get sodium nitrate. So the Na takes the place of the Ca, and there you have sodium nitrate. Each has a valence of 1. Nitrate is a -1, sodium is a +1, and crisscross. Then we have to balance in order to make sure that we have equal number of atoms on either side and also the same type of atoms. So you're going to notice that both your reactants will always be aqueous when it's double displacement, but you're not going to necessarily always have a product that is aqueous, okay? Sometimes we can produce a precipitate. Now we have to use solubility tables in order to predict if our products are aqueous, meaning they stay dissolved, or do they cause a solid chunky material to form in solution. So this is one of the solubility tables that I introduced you to in the intro video, but we're going to use it to help guide us predicting moving forward. So let's just do a little bit of practice with that. So when I'm taking a look at these compounds that are listed below, I want to know, is silver nitrate a compound that stays dissolved in solution, or does it form a solid precipitate? So if we take a look at silver nitrate, I look at the last part of the name, nitrate, and there it is there, NO3, and it says all soluble. So what that means is any positive ions that are hooking up with nitrate will remain dissolved. So that means that this compound is aqueous, and we put AQ. Let's take a look at this next one, phosphate. Phosphate, PO4, there it is there. It says everything is insoluble except for alkali metals. So that means that if you are in group 1 on the periodic table, everything else is insoluble. Potassium is an alkali metal, there it is there. So we know that it is going to be soluble. Since potassium is in that first family, we write down AQ. It will stay dissolved. Let's take a look at sodium sulfate. Sulfate, what are the rules? Well, everything is soluble except calcium, barium, strontium, mercury 2, lead 2, and silver. So we have to take a look, where does sodium fall? Is sodium one of these ions? No. So then it's in this category. So that means that it is a soluble compound. So we write AQ. Let's take a look at barium perchlorate. So that's what this is, ClO4. There's the ion there. Everything that hooks up with that ion is soluble. So we write down AQ. Let's take a look at aluminum hydroxide. So hydroxide is right here. Everything is insoluble, so meaning doesn't dissolve, except if you're group 1 or if you are calcium, barium, or strontium. Well, aluminum is not in group 1, and it's neither of those ions, so it falls into this category. So that means that this is a solid compound. So that's how we use the solubility chart to help us predict whether something is aqueous or solid. So let's take a look. Let's do a few more here. We add them to our balanced equations. We know that in double displacement reactions, the reactants always have to be aqueous. So this is easy. I just go put AQ, AQ. Okay. The reactants have to be dissolved in solution. So let's take a look at our products now. So here we have KBr. So if I go look up here, that's bromide. Everything is soluble except silver, mercury 2, and lead 2. So that means that this is soluble, AQ. Calcium chloride. Chloride, everything is soluble except for those. So this is also AQ. So in this case, we don't get a precipitate. Let's take a look at sodium carbonate. Everything is insoluble except for alkaline metals. Well, this is an alkaline metal. It's in group 1. So I'm going to write down AQ. Let's take a look at copper. Now, is this copper 1 or copper 2? Well, I have to remember that hydroxide is a -1. Copper can be a +2 or a +1. Okay? How do I know that? Because when I go on the periodic table, copper can be a +2 or a +1. This happens to be copper 1 hydroxide, okay, because the brackets were dropped and they had to pick a 1. Let's go take a look. Everything is insoluble except alkaline metals, calcium, barium, strontium. So copper falls into this category. So this compound happens to be your precipitate. So this is how we use the solubility table. When it gets into double displacement reactions, we have two types that occur. You can have precipitation reactions or you can have neutralization reactions. When we have double displacement reactions that produce a precipitate, we have to break it down into the molecular, ionic, and net ionic equations. So let's go ahead and practice these, okay? So when we have lead 2 nitrate and potassium iodide, I'd like to start off with the molecular balanced equation. So lead, they're telling me to pick a +2 for lead, and I know nitrate is NO3. So this is one of my polyatomic ions, which is a -1. We crisscross, and the 2 comes out here. I know that this compound has to be aqueous in order to cause a double displacement. I'm going to react it with potassium iodide. Now, potassium is a +1, iodide is a -1. We crisscross, and we just get Ki. This is also aqueous. What are the new compounds that are going to be made? Well, lead is going to swap places with the potassium because those are both my positive ions. So the lead, because I used a 2, it's going to remain a valence of 2 when it hooks up with the iodide. So if they want me to pick a 2, iodine is still a -1, so you're going to get lead 2. Now, I have to look up whether or not that's aqueous or a solid. Then I'm going to put potassium with the nitrate. Potassium was a +1. We know that nitrate is a -1. Okay, so crisscross, technically I can drop the brackets there. Let's go take a look at our solubility table. Lead 2 iodide. So let's go find, there's iodide, I. Soluble except silver 1, mercury 2, lead 2. Ooh, that's what that is. So I need to put an S here for solid. That is a precipitate. Nitrate, everything is soluble when it hooks up with nitrate. So I'm going to put an AQ there. The next thing that I want to do is I want to balance this equation. So I'm going to put a 2 in front here so that my iodines are balanced. I have 2 potassium now, so I have to put a 2 in front here. I have 2 nitrogens, 6 oxygen, 6 oxygen. So that is nicely balanced. So that is our balanced molecular equation, and that's what we're used to doing, okay? Now, when we get into ionic equations, what we have to do is break these compounds up into the respective ions. So that means I have to show the charge. So I'm going to break this compound up into lead plus 2. So I know that that ion is floating around in solution now, okay? When I see the other ion that makes up that compound, I write that polyatomic ion with its charge, okay? So if it's an ionic equation, you have to show the charges. Notice that there's a little 2 below here. That means that you have 2 nitrates that are going to be liberated for every one of those compounds. So we have to balance the ions. So we're going to put a 2 in front there. Ions are always aqueous, so you still have to indicate the charges there. Plus, we break up this compound. You have potassium ion and you have the iodide ion. Now we still have to write AQ, but notice this coefficient out front. So that means that you have 2 potassium ions and 2 iodide ions. Notice that this is not a Hofbrinkel. Ions are not the same thing as diatomic molecules. So you would not double up the iodine. A charged ion are never Hofbrinkels, okay? Then you always keep the precipitate intact because it's no longer aqueous in solution. So if you'd watched the intro video, you kind of saw that simulation where the ions stay free floating in solution, but the one that forms the precipitate, okay, will then settle out to the bottom. So that stays intact. Then this remains aqueous in solution, so that still remains as ions. So I'm going to put a K plus, aqueous, and the nitrate is also aqueous. I have to make sure the charge goes there. There is a coefficient of 2, so that means that I have 2 of these and 2 of these that are released. This is what is known as the ionic equation. Okay, so anything that's aqueous gets broken up. Then what we do is we cross off what we call the spectator ions. So spectator ions are the ones that are common to both sides. Okay, so I see that I have 2 nitrates, I have 2 potassium ions, and what you should be left with are the ions that make up the precipitate. What we do is we write the positive ion first, and that is the lead 2 ion, reacting with 2 iodide ions, and that will create lead 2 iodide as our precipitate. Okay, now if everything works out, you would see that everything is balanced. If you have plus 2 and you have 2 minuses, those cancel out to yield something that's neutral. So not only do the number and type of atoms on both sides of the equation have to be balanced, but you can also check that by the charges. Okay, so because we have something that's neutral on the right, the charges have to balance so that it becomes neutral on the left. Let's take a look at this reaction so you can see what's going on. As we could see from the video, this led to iodide, your precipitate, was that yellow precipitate. Let's just complete our word equation above. So you are producing lead to iodide, the outside hookup and the inside hookup. So we'll just complete that, making sure that we put our Roman numeral in there, lead to iodide plus potassium nitrate. Okay, I think we should do one more together. Magnesium sulfate and sodium hydroxide. So magnesium is a +2, sulfate is a -2. So when you crisscross, those reduce in terms of their subscripts. Technically, I can drop the brackets. That compound has to be aqueous in solution in order to have a double displacement reaction. Sodium hydroxide, sodium is a +1, hydroxide is a -1. I don't need the brackets. And again, that is aqueous. What we're going to do is we're going to swap the positive ions. Okay, so sodium hooks up with the sulfate, magnesium hooks up with the hydroxide. So if sodium is a +1 and sulfate is a -2, then that means the 2 comes down here. And if magnesium is a +2 and hydroxide is a -1, then that means I have to put hydroxide in brackets, right? Because if that crisscrosses, you need to keep those brackets on. So we have to figure out whether our products are going to remain aqueous or do we have some sort of precipitate. So let's take a look at our solubility table. And this time I'm going to use a different solubility table in my determination so that you know how to use both. So sodium sulfate is what I'm looking for and magnesium hydroxide. When we use this table here, I want to look for sodium. So sodium is right here, and I want to look for sulfate. So I'm going to go across because here's sulfate. And I want to see where they intersect, and I see that it says AQ. So AQ means it is aqueous. Now let's check magnesium hydroxide. Here's magnesium, and here is hydroxide. So what I'm going to do is I'm going to go down and I see they intersect right here. That S means solid. So we can use this table to help us predict. We're going to write AQ here, and this one is our solid. Let's make sure that everything is balanced. I have 2 sodium. I have 1 sodium. So I'm going to put a 2, actually I'll use a different color here, 2 sodiums. Let's take a look. We have 1 magnesium, 1 sulfur, 1 sulfur. Now I move on to hydrogens. I have 2 hydrogens here. I have 2 here. And I have 2 oxygens plus the 4 is 6. Here I have 2 oxygens plus the 4 is 6. So it looks like I just needed a 2 in front over there. Okay, now the tedious part. We have to break everything up into ions. That is aqueous. So magnesium sulfate, what that means is we have a bunch of magnesium ions floating around in solution. We have a bunch of sulfate ions. Sulfate is a -2 floating around. We have a bunch of sodium ions floating around. And we have a bunch of hydroxide ions floating around. We have to balance because there's a coefficient of 2. We have 2 sodiums and we have 2 hydroxides. That yields sodium ion, and that is aqueous, sulfate ion. Now, hopefully you noticed that there is this subscript of 2. So for every one of these compounds, 2 sodium ions are liberated. So you've got to put a 2 there. And then what we do is we leave the precipitate intact. So we do not touch that one. Okay, we don't break it up into its respective ions. So what we're going to do, we're going to cross off our spectator ions. And what we are left with are the ions that make up the precipitate. So we're just going to rewrite that as Mg plus 2 ion plus 2 hydroxide ions, yielding my precipitate of magnesium hydroxide. Okay? Does everything balance? One magnesium, two hydrogen, two hydrogen, two oxygen, two oxygen, a +2, and then two minuses yield neutral. So we have our net ionic equation. Let's take a look at this reaction. So there we have that precipitate reaction. Okay, we're going to move on to the second type of double displacement reaction called neutralization reaction. So here we are with our neutralization reactions, and we know that those involve an acid plus a base yielding some sort of salt and water. Okay, so the key here is to recognize whether or not you have an acid and a base as your reactants, and you would classify this more specifically as neutralization. Okay, so it's just a subcategory. So here we have hydrofluoric acid. Remember that when we have a binary acid and it's hydrofluoric, you just write down H and the halogen that hooks up with it has to be aqueous, and same with your base. If it ends in hydroxide, more than likely you've got a base. So what we do is we're going to swap the positive ions out. So the H is going to hook up with the OH, the Na is going to hook up with the F. So in this case, the Na is your positive ion, the hydroxide is your negative ion. Here, the hydrogen is your positive ion, the fluoride is your negative ion. So if sodium has a charge of +1, fluoride has a charge of -1, you get sodium fluoride. That will remain aqueous, and then you get the H and the OH hooking up. If hydrogen is a +1, hydroxide is a -1, you just get HOH, which we refer to as water, okay? And that will be liquid water. Only if we evaporate that water can we get this salt to form in solid form, okay? So salts are anything that generally end in "ide," "ate," or "ite" in their name. So the salt in this case is sodium fluoride plus water. Okay. Over here, we've got, and this is all balanced now, so that's perfect. Now let's take a look at this acid-base combination. Here is sulfuric acid, H2SO4, and here's barium hydroxide. So again, the positive ion, which is always the first part of the compound, those guys are going to switch places. So barium is going to take the place of the hydrogen here. We're going to take barium and we're going to hook it up with sulfate. Remember that when we make new compounds, we have to go back and check the valences. So sulfate is a -2, barium is a +2. So when you crisscross, you can drop the brackets because they would have a common subscript. Okay, so in this case, that salt will be aqueous, and the H hooks up with the OH, and you just get water. So this happens to be barium sulfate plus water. Now, when we want to balance this, we want to take a look. We have one barium, one barium. We have one sulfur, four hydrogens. So we have to put a 2 here because there's 2 here and then there's 2 here. And then we have 2 oxygen plus the 4 is 6. Here I have 4 and 2 is 6. Okay. Last one, phosphoric acid and calcium hydroxide. If you're not sure what the formula is for phosphoric acid, you do have a chart that you can refer to that I have put as a resource in this section. Let's take a look at that. So in this section, you can see that the common acids I have linked here. I'll just move that into a new tab so you can see. So phosphoric acid is right here. So that is H3PO4. When we are writing the formula, we're going to write down H3PO4 must be aqueous. Calcium hydroxide is CaOH with a 2, okay? Now, you can't really come up with the name using the reactants, so there's no such thing as phosphoric hydroxide and calcium acid. Because sometimes, when we do our double displacement, we just swap the partners and we can come up with the names, okay? But when you're dealing with acids and bases, you kind of need to do the molecular equation first to figure out what the names of your products are going to be. So hydrogen hooks up with the hydroxide. So you write the water. Now, notice that I wrote water first this time. It doesn't matter. This is just my italicized L for liquid. It doesn't matter if I write water first and then my salt, as long as they're to the right of the equation. Calcium is hooking up with the phosphate, because remember, just the hydrogen and the calcium are swapping spots. So if calcium is hooking up with the phosphate, okay, we're going to go and take a look. Calcium is a +2, phosphate is a -3. So when you crisscross, the 3 comes here and the 2 comes outside of the bracket. That salt remains aqueous unless we evaporate the water, in which it will become a solid. We have to do some balancing here. 3 calcium, 1 calcium. We've got 2 phosphorus. We only have 1 here. So I've got to put a 2 out front. Let's take a look at our hydrogens in total. We have 6. And here I have 1 hydrogen in the bracket times the 2 outside the bracket times the 3. So 2 times 3 times 1, I have 6. And then over here I have 6. So that's 12 hydrogens in total. Over here, I only have 2. So I need to put a 6 here. Let's take a look at our oxygens in total. So oxygen here, I have 8. And over here, I have 1 times the 2 times the 3. So 1 times the 2 times the 3, I have 6. So that gives me 14 oxygens in total. And over here, I have 6 plus the 8, that gives me 14. So this is balanced. So what do I write as my products? You have water plus calcium phosphate. Okay, so time for you to do a little bit of practice. Really important that you reach out if you need more clarification. I do have the answers posted for some of these double displacement reactions, so please cross-check your answers before doing the evaluation.